Good morning, everybody. So we're going to pick up today's lecture where we left off in last lecture. Oh, hang on. Sorry, I'm trying to adjust the volume here, but I have no control over the volume. Okay. All right, so we were talking about floating point numbers and how they're represented on your computer, or I guess quote-unquote real numbers and how they're represented on your computer. So Java has two floating point types. There's float and double. They both come from this standard called IEEE 754. So the standard says float is the standard says that you can have a 32-bit floating point number or a 64-bit floating point number or larger. So there's 128-bit floating point numbers as well. So Java calls the 32-bit version float, and it calls the 64-bit version double. In Python, everything is just 64 bits, and it's called float, short for floating point. Now, I guess it would be informative to actually study how these types, how the IEEE standard says these numbers ought to be represented, but it's very awkward, right? Every time I want to write down a floating point number, I have to write down 32 or 64 zeros and ones. Right? And that's no fun, right? So you don't want to watch me try to scribble down 32 zeros or ones, right? Also, most people aren't used to reading binary, right? So we're used to working in decimal, and so it would be nice if we could study this and work in decimal instead of in binary. Now, fortunately, the standard says there is a standard for decimal values as well. So that's nice. But we're not going to look at that either. Instead, we're going to look at a reduced version so that we can actually write down numbers in a convenient way. All the ideas are still the same as what's in the standard. Right? So instead of using 32 or 64 zeros and ones, I'm going to use 4 decimal digits, so 0 through 9. Right? And so our representation is going to look like this. So we have 3 decimal digits, right? So values between 0 and 9. Right? The first value, for simplicity, we're not going to let it be 0. Right? So in other words, D1 has to be at least 1. We're not going to worry about the sign. Right? The standard actually specifies how the sign is represented. We don't care. We're just going to write down plus or minus. And then over here, there's an exponent. Right? So our number is going to be some integer value times 10 raised to some exponent here. Now we want to use one digit up here to represent the exponent, so a value between 0 or 9. If we want values less than 1, we need to be able to make this exponent negative. So our value d4, we're going to subtract 5 from it. So if d4 is between 0 and 9, the total exponent is between minus 5 and 4. Right? And so that's what our numbers are going to look like. So that looks a lot like this, right? So back here, right? That's the binary representation of a floating point number, some integer times 2 raised to some exponent, right? Ours is some integer times 10 raised to some exponent. Right? Okay, so if you start to scribble down what numbers can I write down, or what numbers can I represent using this representation, you get a table that looks like this. So what's the smallest positive value that you can write down? Well, our first digit has to be a 1, right? If I want the smallest number, the next 2 digits have to be a 0, right? And now I want my smallest exponent, so that's minus 5, right? And if you scribble that out in decimal, you get 0.00100. So that's the smallest positive value I can represent. Right? If my value is less than 0.001, there's no way for me to represent it exactly. Right? I don't have sufficient number of digits to do so. So the next question you can ask is, well, what's the next number I can write down and represent exactly? Right? Well, that's just 101 times 10 to the minus 5. So that's 0.00101. If there's a number in between these two that I want to write down, I can't write it down exactly, right? I'm stuck using either this one or this one, right? So if I'm closer to 0.001, my number gets converted to 0.001. And if I'm closer to 0.0101, I end up representing the number as 0.00101. Right? And so right away you can see that there's an impact of, caused by the fact that we have a finite number of digits to represent our number. Right? There's a lot of values, or there's an infinite number of real numbers between these two values that I can't represent. Right? There's some smallest positive value. There exists some smallest positive value. Right? Any value between 0 and that value I can't represent. So if you look at the difference between these two values, right, you'll see if you compute it mathematically, it's 0.00001, right, the difference between these two values. But if you pay attention to what's happening in the last digit, right, because our digits start with an integer, adjacent numbers always differ by 1 in the last unit. Right? So in this unit, in the digit to the on the far right, right, the next, they always change by 1. So the next value would be 102 times 10 to the minus 5, right? And that would be 0.00102, right? And so the distance between adjacent floating point numbers is always 1 unit in the last place. Right? So that's called an ULP, right? The ULP is the distance between adjacent floating point values. Right? Oops, sorry. Now notice that the value of an ULP, so the magnitude of an ULP changes depending on the magnitude of your number. Right? So here I've got something times 10 to the minus 5, and ULP is 1 unit, right? But that unit is equal to 0.00001. If the exponent changes to minus 4, right, then the value of an ULP changes to 0.0001, right? So in other words, the distance between two adjacent numbers changes depending on the magnitude of the exponent, right? The ULP, so I guess it's important, so the ULP here is still 1, right? The difference in the unit in the last place is still 1. The difference here is still 1, right? When you actually compute its magnitude in decimal, the value changes. Right? So not only are there only a finite number of of floating point values, right? The distance between floating point values changes depending on its magnitude. Right? If you go all the way up to the largest value, to exponent 4, right? The smallest value that you can represent with an exponent 4 is 1 million, right? So 1 with 6 zeros after it. Right? The next smallest value that you can represent is 101 times 10 to the 4, which is 1,010,000, right? So if you had 1,000,001, you can't represent it exactly, right? Even if you had 1,005,000, you can't represent that exactly either, right? You end up using either that value or that value, whichever one is closer. Right? And so right away you can see that floating point numbers are strange, right? And it all comes from the fact that you only got a finite amount of memory to represent each value, right? Fixed and finite, right? And this is so this is the reality of the situation that happens when you're doing floating point arithmetic on a computer, right? Okay, so the ULP is the distance between adjacent floating point values, right? The magnitude of that value changes depending on the magnitude of your exponent. Right? When people talk about errors when using floating point numbers, they often talk about errors in ULPs. Right? So if you want to know what is the magnitude of an ULP, you can ask Java for it. Right? So if you have some value, I would like to know what is the value of an ULP for 1.0, you can call the method math.ULP and pass in 1.0. And Java will tell you what is the magnitude of an ULP for the value 1.0. Okay, so if you're working with floating point numbers, you might start out with a problem where you have some value that you know, right? So suppose you start out with the value 1 or something like that, right? You compute some value that you also expect to be 1, right? So I'm expecting my true value, x hat, to be 1, right? I compute some other number that I expect to be 1, right? So that's x. And I would like to know what is the error between those two values, right? So the error is just x hat minus x, and then you take its absolute value, right? So that's the error between the two values. It's called the absolute error. Right? So when you're working with floating point numbers, you end up with an error almost immediately. When you write down your floating point number, there's a high probability that it can't be represented exactly in your floating point format. Right? And so 0.2 has no exact representation in binary. Right? And so that means that the number that we start out with wasn't really 0.2. There's some error. So when you convert a real value into to its floating point value, so when I convert 0.2 to a double on my computer, right, the IEEE standard says you must be within 1/2 an ULP when you do that conversion. Right? You might say, well, why do I have to be within 1/2 an ULP? Well, it makes sense, right? So we go back here to the table, right? So suppose I have the number 1,000,001, right? I can't represent 1,000,001 exactly, so I have to pick one of the two numbers that it's between, right? And use that to represent 1,000,001. And so in this case, obviously, I'm going to choose 1,000,000. What's the error in ULPs? Well, 1,000,001 minus 1,000,000, so there's a 1 all the way over here, right? And so the error in ULPs would be 0. Well, you want to compute it using this digit here, so it'd be 0,0,0,1. So 0.00001 ULPs of error, right? Eventually, if you get to 1,005,000, you have to pick one of these two values, right? And so your error is going to be 5,000. So that's a 5,0,0,0. And so your error in ULPs will be 0.5, right? You're exactly halfway between two numbers, two floating point numbers. Right? And so when you convert any number to its floating point representation, that conversion has at most an error of 1/2 an ULP. Right? You end up, your actual number is halfway, but is at worst halfway between two floating point values. Okay, so suppose you're not worried about conversion, but instead you want to know what is the error, or you're interested in calculating the error between a computed value and its true value, right? And then there's a recipe for computing its error in ULPs, right? And so what you do is you take your true value and you write it using our floating point representation, right? So I write it using 3 digits times 10 raised to some exponent, right? And then you do the same thing with the other value. Right? Now, when you do the same thing with the other value, with x, right, the thing that you have to remember here is that you must use the same exponent that you used when you wrote down the true value. Right? And so we'll see examples of this shortly. Right? And now you simply take the difference after writing down their values in your floating point format. Right? So for example, I have a true value of 1.29. Right? And I have a computed value of 1.25. Right? I want to know what is the error in ULPs. Right? So I compute its absolute error. So I start out by writing 1.29 in our floating point format. Right? So I need 3 digits, so it's 129. Right? Multiplied by 10 to something. So now you compute the something. Right? So here it has to be minus 2. So that you get 1.29, right? And you do the exact same thing with the 1.25, and you make sure that when you write down 1.25, right, you write it out with that exponent. So this one's easy, the exponent's the same. Like that, right? And now you just take the difference here. Right? So you do your subtraction, and you get 4 times 10 to the minus 2. Right? That number there is your error in ULPs. Right, so the unit in the last place of this number here, right there, is your error in ULPs. Now, it's a little bit deceiving. So if this number were bigger, then that whole thing would be the error in ULPs, right? Okay, so the key part here is to make sure that those two exponents are always the same. Right? Okay, so here's an example where when I write out these two numbers in their floating point format, if you were to just write them out on their own, you would get two different numbers. Right? So here we have 12.1 and 0.5. Right? So 12.1 is 121 times 10 to the minus 1. Right? 0.5, if I was to write it out in our actual floating point format, would be 500 times 10 to the minus 3. Right? So when you're computing the error, you don't want to write out the measured value or the computed value in its correct format. Right? You want to convert its exponent to minus 1. Right? So you want to do something times 10 to the minus 1. Right? And if you scribble that out, it would be 5, right? Times 10 to the minus 1. Right? And so now you do your subtraction. Right? And so when you do your difference, you get 116 times 10 to the minus 1. And so now you have a difference of 116 ops. Right? The reason you're making sure the exponent is the same is because I want the error relative to the 12.1. Right? So in other words, I want to compute its error in ops, right, relative to the exponent, in this case, minus 1. Right? Okay, so often it's the case where, well, not often, sorry. Sometimes it's the case where your true value is a real number as opposed to some floating point number, right? So imagine you're working on some mathematical problem and you know that the true value that you're computing should be equal to pi, right? Pi has an infinite number of digits, right? So how do you write that down in your floating point format? And the answer is you don't really, right? So you write down, in this case, I'm using this giant number here, right? I'm going to write it out in our floating point format, but I'm going to keep all of the decimals, all of the digits after the decimal, right? So you only do this for the true value. So for your true value, I'm now going to write out 592.87 blah, 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 right? So I'm going to use more than 3 significant digits here, right? For your second value, though, you're going to write it out correctly in our floating point format. So I'm only going to keep 3 digits for it. So that's 589 times 10 to the 2. Right? Now you do your difference, and it's 3.8 blah, 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 ops. Right? So it can be the case that your true value, x, right, has more than 3 significant digits in it. And if that's the case, just keep them all. But remember, always write it out as some 3-digit number times 10 to the, some 3-digit integer part times, times 10 to some integer exponent. Okay, you may occasionally come across the relative error, especially if you're in the sciences, I guess particularly physics and chemistry, maybe bio, I guess. So the relative error is the absolute error divided by the true value. Right? So if someone asks you to compute the relative error, you don't go through all of this rigmarole of writing things down in our floating point format, right? You just compute this as though it were actual regular mathematics, and away you go. That's all I'm going to say about relative error for now. Okay, so how does addition and subtraction work with floating point values, right? And so the way it works is if you write out your two values that you're adding or subtracting using your floating point format, right? So here I've got 12.1 and 63.8. So what's 12.1 in our floating point format? Well, it's 121 times 10 to the minus 1. Right? What's 63.8? Well, it's 638 times 10 to the minus 1. Right? The exponents are the same here, so I can just add the two numbers just like you would in grade school. Right? So add those two values, it's 759 times 10 to the minus 1. Right? If it's subtraction, it's the exact same thing, right? Just subtract the two values. Here's another example, so 81,500, right? 13,600. Just write out your two numbers in our floating point format. So 815 times 10 to the 2, 136 times 10 to the 2, and just add the two integer parts. Right? Exponent stays the same. So that's 951 times 10 to the 2. Okay, now obviously if you're adding two values, you might end up generating an extra digit. Right? So if you add two values whose integer parts are both bigger than 500, right, you're going to end up with an integer part that's greater than 999, right? And so what do? Well, you compute. You just do the exact same thing, right? So you write down 82.1 as 821 times 10 to the minus 1, right? You write out 63.8 as 638 times 10 to the minus 1. Go ahead and add. So this is our intermediate result now, right? So you take the sum, and you end up with 4 digits. The problem is, in our floating point format, we've only got 3, so I can't keep them all, right? And so we're going to say you round this value here, right? So you round it to the nearest second digit in this case, right? So this becomes 1460 times 10 to the minus 1, right? Which you can write properly using 3 digits here as 146 times 10 to the 0. Right? And so your final result is that, right? And notice that number there is not correct, right? It's not actually equal to the sum of 82.1 and 63.8, right? It should be 145.9, but it's not. We can't represent 145.9 in our floating point format. So we end up computing the value 146 instead. Right. Another example here, right? Write both numbers out in our floating point format. Compute the sum, too many digits, right? Round to the nearest second digit here, right? So this becomes 175 times 10 to the 3, right? Exponent goes up by 1 in this case. Right? So if you ever compute a value and there's too many digits in it, we're going to end up rounding that intermediate value and only keeping the 3 digits. Okay, so what happens if the two values have a different exponent? Right? And so the rule is still the same as before when we computed the error. Right? It's not exactly the same. You're going to look at the number with the largest exponent, and that's the exponent you're going to use when you write down your other number. Right? So if the two values have different exponents, then you use the exponent, then the one with the smaller exponent, you have to scale it so that the exponents become the same. Right? So 4,320,000 is 432 times 10 to the 4. Right? 12.1, if you were to write it out properly, is 121 times 10 to the minus 1. Right? I need to make these exponents match because what I want to do is basically I want to just sum these values here, right? So I can sum those values there using grade school math because the exponents are different. So I have to make this exponent the same as the other. I make the smaller exponent the same as the larger exponent, right? So the 121 becomes, well, it looks like I have to shift the decimal 5 places. So 1, 2, 3, 4, 5. So it's going to be 0, 0, 0, 0.00121 times 10 to the 4. Let's make sure I did that right. So 1, 2, 3, 4. And the answer is yes, I did it right. Right? Did I do it right? 0, 0, 0. Yeah, that's right. Okay. Right? And now you can sum that number and that number. Right? So the exponents are now the same. And now you can go ahead and compute the sum to get the value on the slide. Right? So your intermediate result becomes 432.000121. And now, again, in the same, you have the same problem as before. Right? I'm only allowed to keep 3 significant digits. Right? I need 8 to actually represent the true value. Our floating point format only has 3. So we have to compute or discard everything after the decimal in this case to get 432 times 10 to the 4. Right? So you can either discard all the digits, so just ignore them, or you can round. So if that's like a 5, you can round the 2 to a 3. It doesn't matter which one you do in this course. I don't actually know what real computers don't do it exactly this way anyway. Right? But it's close enough for our purposes. Right? And so now you get 432 times 10 to the 4. Right? Now, look at your final answer. Right? 432 times 10 to the 4. Right? Look at the two numbers that you added together. Right? So the first number that I added together was 4,320,000. But that's 432 times 10 to the 4. Right? The second number is some positive value. Right? And so what's happening here is that you've got x plus y, where x and y are both positive, and the result is equal to x. Right? That number there is the same as that number there. So when I compute the sum, it's as though the 12.1 never existed in the first place. Right? X plus y equals x, y is not equal to 0. Right? So mathematically, this makes no sense, but this is what happens in floating point. Right? So all the stuff you know from mathematics, it's only approximately true when you work in floating point. Right? And you end up in strange situations where what makes sense mathematically doesn't make sense when you actually compute it on the computer. Right? Why does this happen? Well, I have a limited number of bits to store my values. Right? It's limited and it's fixed. So you're going to run into situations where you compute a value and it doesn't fit. And so you try to compute a value, and when you convert it to your floating point format, it doesn't give you the value that you expect. Right. Okay, so, what would you do here? Okay, so it might be possible that you, in your representation, we're going to use 3 digits for the significand, we're going to use 1 digit for the exponent, right? But when you're doing these calculations, it might be useful if you had some extra digits, right? So maybe in this case here, it wouldn't actually help in this case here, right? So unless I had, it doesn't matter how many extra digits I have in this case here, I'm always going to end up with 432 times 10 to the 4 when I convert it back to our floating point format. But you can imagine there might be situations where if you had an extra digit in the intermediate result, you might be able to get a better final result, right? So it would be nice if we had extra digits, right? But you have to remember that when you're doing these calculations, all of this stuff is happening in hardware. So in your CPU, when you're adding these two numbers, it's all being done in hardware. So there's no way that you can just stick extra digits in hardware. Well, there's no easy way to do it, right? And in fact, in the very early computers, it wasn't possible at all. Turns out that on modern CPUs actually use extra digits to calculate the intermediate results. Okay, so what do we do with these extra digits? Right? So I said, in this case here, I said you could round or you could discard, right? Oh, sorry, instead of back here, right here. So when I computed this result here, when I wrote down y, I kept all of the extra digits here. In our floating point format, we actually don't have all of these digits after the decimal point, right? And so I really shouldn't be keeping these digits when I compute the result, right? And so instead of keeping those digits, what happens if I just get rid of them, right? So instead of writing 0.0.00121, I throw away everything after the decimal point, right? And to get 0, so now you get 0, 0, 0 times 10 to the 4. Right? And so now when you do the sum, it's like you were doing 432 plus 0. Right? And so now this kind of makes sense, right? This is why when I sum these two values, I just get back the first value. Right? If you're allowed to keep extra digits here, it's possible that you get a better final result. Right? So with addition, everything happens the way I showed you. Funny things happen when you perform subtraction. So here we've got 10.5 and 9.98, right? So notice here the values were, the values here are dramatically different, right? Their magnitudes are very different. Here the magnitudes between these two numbers is not very different, right? The difference between these, the actual difference here is just 0.52, right, which is not very large. But when you actually compute the difference here in our floating point format, right, we get 10.5 becomes 105 times 10 to the minus 1. Right? Now this 9.98, right, becomes 0.99.8 times 10 to the minus 1. Right? So if you believe that, or so if you are in the situation where you can't keep that 0.8, so I have to get rid of it somehow, right? So we throw it away, and now you compute the difference, right? You get 6 times 10 to the minus 1, right? Which is 600 times 10 to the minus 3, right? What's the true answer here, right? So 10.5 times minus 9.98, its true answer is 520 times 10 to the minus 3, right? So notice we're in a strange situation here. I can write down the true answer in our floating point format without losing any precision, right? But I can't compute this value here to get the true answer, right? When I compute it, I get 600 times 10 to the minus 3, right? If you take that to be the true value and you subtract 600 times 10 to the minus 3, you get minus 80. Take its absolute value, that's 80. Right? And so the error between that number there and that number there is 80 ULPs, right? Which is enormous, right? The IEEE standard says if you subtract, if you do any arithmetic with two values, the final value should be within 1/2 an ULP of the true value, right? So we should be within 1/2 an ULP, but instead we're 80 ULPs away. So almost 2 orders of magnitude. More than 2 orders of magnitude away from the true value. Right? So that's no good. So it looks like if we throw away the extra digits that we need to write down y, we're going to run into problems. So what do? So in modern hardware, what ends up happening is when you are computing the intermediate values here, you are allowed to keep a small number of extra digits. So I think Intel CPUs keep 16 extra digits or something like that. I think they do the arithmetic with 80 bits instead of 64 for double. So for our purposes, let's keep 1 extra digit. Right? What does this say? Okay, so that discard extra digit should not be there. Sorry, that's a cut and paste error. Keep 1 extra digit. Right? So instead of throwing away the 8 in this case, right, we're going to let an extra digit exist for temporarily to compute the result. So 105 becomes 105.0, 9.98 becomes 99.8. Right? Now compute the intermediate result to get 5.2 times 10 to the minus 1, right? And now I can convert that value back to its correct floating point value, which is 520 times 10 to the minus 3, right? And so converting that number back to its correct floating point value is called normalizing, right? You might have to round as well in this case, but we don't have to in this case. So you get 520 times 10 to the minus 3, and that's equal to the exact result. Right? So even though we can't really write down 10.5 and 9.98 exactly when we convert them both to the same exponent, right? If we keep 1 extra digit, we can, right? And that lets us compute the correct final result, which is good, right? We went from 80 ULPs of error to 0 ULPs of error just by keeping 1 extra digit, which is nice. So it turns out that if you use just 1 extra guard digit, it's not enough to guarantee that 1/2 ULP of error, right? So for example, here's 110 minus 8.59, right? Write out 110 in our floating point format. Well, it's easy. It's 110 times 10 to the 0. Right? 8.59 is 859 times 10 to the minus 2. Right? Make the exponent the same, right? So that becomes 8.5, now there's a 9, right? So with that second extra digit, we're not allowed to use it. So we're going to throw it away, right? So instead of 8.59, it's 8.5. We can't keep the 9, right? We've already got the extra digit, that's why we're not rounding, right? So to round, you'd need a second extra digit. We don't have it, so we only have 8.5. Right, now do the difference and you get 102 times 10 to the 0. Right, the true answer is 101.41. Right, and so if you compute the difference between these two values, it's 0.59 ULPs of error, which is slightly more than the 0.5 required by the IEEE standard. Right, so it turns out you need 2 guard digits in this, for our little format, our floating point format, to ensure you get 1/2 an ULP error when you do simple arithmetic. Well, when you do addition and subtraction. Not clear what happens when you do division and multiplication. Right. Okay, subtraction is in particular is strange when you are working with floating point values. Right. So when you subtract two floating point values, you end up with what's called, when you subtract any two values, you end up with what's called cancellation or loss of significance. Right. This says when you subtract two floating point values, but mathematically, if you subtract two values, you end up losing significant digits. Right. So here's a 10-digit floating point number. Here's another 10-digit floating point number. Right. They only differ by 1. Right. So when you compute the difference, so I take x subtract y, I end up with 1 times 10 to the 0. Right? Notice there's 9 significant digits in x. There's 10 significant digits in y. Right? The difference has only 1 significant digit. Right? So you end up with this what's called cancellation or loss of significance, which is not surprising. The magnitude of your difference is smaller than the original two values. Right? So in this case, the difference has 1 significant digit, even though the operands have 9 and 10 significant digits, respectively. Okay, so this is called cancellation because your leftmost digits, or your high order digits, or your most significant digits cancel one another out, right? So in other words, that 1 cancels that 1, that 2, well, I guess I should work the other way around. There's cancellation here, 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 and here, right, all the way up to the 1. Right? These values are canceling each other out because that's the way subtraction works. Right? So all of your significant digits on the left, from the left of the number, they all become 0 or smaller anyway. Right? And so you lose all the significant digits on the left-hand side of the number. Right? So this isn't strange. This is just the way subtraction works. Right? So this is not a problem if your two values contain no error. Right? You subtract the two values, you end up with the correct result, right? And so this is called benign cancellation. So cancellation always happens when you subtract two values because that's the nature of subtraction, right? If your values have no error, there's no problem, right? You compute the difference, it's the correct value. And so we say that the loss of digits is not important, it's benign, right? That's not true when your two inputs have some error. So catastrophic cancellation occurs when one of your two operands contains some error, right? Now, when might your inputs have some error? Well, they almost always have error in them when you are working in floating point, right? Just writing down the number itself might end up in error because you can't convert the decimal number to binary. Right? If you compute two floating point values and subtract them, then you end up, then it can be the case where you end up with an answer that is very far off from the correct answer. Right? So I want to compute the roots of a quadratic equation. Right? So you pull out your quadratic formula and you say, well, I need to compute b squared minus 4ac. Right? So here I've got some, I just made up some numbers. So b is 3.34, a is 1.22, c is 2.28. Notice I can write down all of these numbers exactly in our floating point format, right? There's no issue. They all have 3 significant digits. Okay, so I'm going to work out the correct answer, not in our floating point format, but I'm going to work it out mathematically. Right? So I compute b squared minus 4ac, and I get 0.0292. Right? So the value of b squared minus 4ac can also be written down exactly in our floating point format. So I can write b exactly, I can write a exactly, I can write c exactly, and I can write the correct value of b squared minus 4ac correctly in our floating point format. If you look back here on the second line here, you can tell that you can't compute it exactly, right? I need 6 digits here and 6 digits here, and I've only got 3, 4 if I include the guard digit, right? So something funny is going to happen in that step there. Okay, so what's the something funny that happens? Well, I have to compute b squared in our floating point format, right? So b squared is really 111.556, but I can't do that exactly, right? I can't write down the 556, right, when I compute b squared. The absolute best that I can do is hopefully I can compute 111.5 and then round that to 112, right? So that's the absolute best that you can do. So I'm trying to make this the absolute best situation possible for our floating point standard, our floating point format. The same thing is true for the 4AC, right? Its exact answer is 111.264, right? The absolute closest that I can get in our floating point format is 111 times 10 to the minus 1, right? So that's the best case scenario for b squared. That's the best case scenario for 4AC, right? Now subtract them, and you get 1 times 10 to the minus 1, which is 100 times 10 to the minus 3, right? None of the digits in the answer are correct, right? I can't even get the 2 correct. It's 1 in this case, right? So that's 100, that's 292, right? None of those digits are correct. The exponent's not correct. That's minus 4, that's minus 3, right? So I can't even get the correct exponent in this case, right? And the error between that and that is enormous in terms of the number of ALPS. Right? And so there is an example of catastrophic cancellation, right? You compute 2 floating point values. The computed values now have some error. When you subtract them, because of cancellation, the final result ends up being very far away from the result that you expect, right? The true error is 708 ALPS, right? Which is very large. Okay, so if you are reading the notebook, and you read the floating point notebook, the notebook shows you some cases where you might be able to change your calculation to avoid the cancellation, right? You don't need to know that for the purposes of this course, right? If you're curious about if you're interested in this sort of stuff, go read the notebook. It'll show you that sometimes if you're calculating some sort of mathematical formula, you can manipulate the formula to remove the error, or to remove the catastrophic cancellation, right? There are some examples that you can work through. I don't care if you work through them or not. Right? Okay, so the last little bit I want to say about floating point numbers is that we've only added 2 or subtracted 2 values, right? When you're working on the computer, you often have to compute stuff where you have to sum or take the difference of many values, right? Or you have to perform many arithmetic operations to get the final result, right? Every time you perform a simple operation, right, the intermediate result can have up to 1/2 an ALP of error, assuming your computer is following the IEEE standard, right? If it's not, you might have more than 1/2 an ALP in error, right? So if you repeat an operation many, many, many times, or you have many operations in a row, those errors accumulate. Right? I have a 1/2 ALP error, then another 1/2 ALP error, then another 1/2 ALP error, and so on and so on and so on, right? If you're doing lots and lots and lots of operations, you may end up with a value that's that has a very large error. Most of the time, or on average, the errors tend to cancel one another out, right? So your one value might be a little too high, the next value might be a little too low, you add them together and the error goes, right? So it might, so you don't always get a huge error after performing many operations in a row, but sometimes you can, right? Now, so what is the operation that most of you are familiar with where you might have to do things over and over and over again? Well, it's if you compute an average value, right? I've got lots of numbers, I want to compute its average, I have to sum a bunch of values together. So here, I'm going to sum 1,001 values together. Right? I'm using float because float, it's a little easier to see the errors with float than with double, right? Float has fewer digits of precision. Right? So I'm going to take my array, I'm going to put in 1,001 0.1s, right? And then at the beginning of the array, I'm going to replace the 0.1 with 1,000,000, right? So I'm going to compute the sum 1,000,000 plus 1,000 0.1s. right? 1,000 0.1s is 100. So the sum should be 1,100,000, right? Write your loop to compute the sum, and it prints out 1,125,000, right? So it looks like Java can't even compute 1 million plus 0.1 1,000 times correctly, right? That number there is pretty far off of that number there, right? Okay, so it turns out in this particular case, you can compute the exact sum correctly just by moving the location of the 1 million, right? So exact same code, except this time I'm going to put the million at the end of the array, right? Now I'm going to compute the sum, and if you run this, you get exactly 1,100,000, right? And so what's going on here, right? You just have to look at the order in which the numbers were summed in, right? So the first sum starts out with 1 million. Right, so when you add 1 million and 0.1, the 0.1 is a lot smaller than 1 million. So when you compute that sum, you don't get all of the 0.1, like I showed you earlier in the lecture, right? So that value there is smaller than 1,000,000.1, right? And now you add another 0.1, right? So that 0.1 is much smaller than the sum of the two values there. So you don't manage to add all of that. You can't keep all the digits in that 0.1. You lose some of them, right? And so now that sum there is smaller than 1,000,000.2, and so on and so on and so on and so on. If you put the million at the end, right, the problem goes away. Well, it doesn't quite go away, but it becomes, the errors become much less, right? So the magnitude of the first 2.1s, it's the same, right? Their exponents are the same, so when you sum these two things together, the result is very, very close to 0.2, right? And now add 0.1, so it's very, very close to 0.3, all the way up to the end, right? We're very close to 100, and now we add it to 1 million, right? 1 million is much closer, 100 is much closer to 1 million than 0.1 is to 1 million. So when you compute that final sum, it turns out in this case to be the correct sum. And so if you look online, people will tell you if you're computing an average and it's a very long, and you have a lot of numbers, you should sort your numbers first, right? And that will hopefully prevent this problem where you end up summing a large value and a small value right away, right? There's a problem with this. Right? So number one, if you sort your array or collection of values, that changes the ordering of the array or collection of values, which you might not want to do. Right? Imagine you have a spreadsheet and you want to sum the first column, right? And to sum the first column, I have to sort that column, right? And so you might not want to do that. You might want to keep your original data in the order that was in. So now I have to make a copy and then sort the copy, right? Furthermore, sorting has complexity, best case complexity, n log n, which hopefully they told you in 121, right? But I'm just summing n numbers. So really, this operation should only take O(n) time. And it turns out someone actually worked out how to do this without having to sort your original data. And so the person who figured out how to do this is, his last name is Kahan. He's one of the architects of the IEEE standard, and he's also Canadian. And so he figured out how to do this quite a long time ago now. Right? If you want to know how that algorithm worked, again, look in the notebook for it. The details of the algorithm are there. There's an example that you can run. I'm not going to ask you about it, but it's all there for you if you want to find out about it. Okay, so that wraps up floating point numbers. That's all I have to say about it.